Everything that we see and feel around us is usually termed as matter. By now, we even know that matter is classified into 3 major states. And what are these 3 states of matter? That's right, they are solid, liquid, and gas. But have you ever thought about what the matter around us could be made up of? Well, this question is not new and has been addressed a long time ago. And many people have made an attempt to answer it. Let us have a look at a few of these philosophies and theories. Recorded evidences suggest that around 500 BC, an Indian philosopher named Maharishi Kanad hypothesized a concept. His curiosity about components of matter made him put forth an idea. He suggested that when we divide matter into tinier particles, ultimately we reach a stage when the matter cannot be divided further. These particles which cannot be divided further make up the matter. The matter was called Padarth in the Indian language, and he named the particles as Parmanu. On similar lines, another Indian philosopher named 𝓗𝓵𝓵 𝓔𝓿𝓮𝓻𝓂𝓷𝓮 made slight modification in Maharishi Kanad's work and elaborated, saying that such indivisible particles come in different combinations to make up different kinds of matter. Around the same era, 2 Greek philosophers also suggested the same concept. The 2 personalities were Democritus and Leucippus. They also postulated that if we divide matter continuously, then we reach a stage where it cannot be divided further. These indivisible particles does make up the complete matter. Democritus named these particles as atomus, meaning indivisible. Now you may say that this concept is known to us. Yes, I agree, but we are familiar with this concept now. In the era when people were not really aware of anything in science, such concepts proved useful in laying the foundations for modern inventions. Around the end of the 18th century, a few scientists could prove these suggestions correct. They not only discovered, researched about atoms, but also threw light on the basic difference between elements and compounds. Yes, studying this difference paved the way for many scientists to understand how several combinations can lead to the formation of different substances. But now when I say combinations, it means we will have chemical reactions, right? That's correct, and chemical reactions are governed by a few important laws. This fact was understood and accepted widely when foundations of chemical sciences were laid by the French nobleman and chemist Antoine Lavoisier. The 2 most important laws of chemical combination were established by then. They were popularly known as the law of conservation of mass and the law of constant proportions. Let us take a look at both these laws in the upcoming videos. Chemistry gives answers to many queries. It acts as a bridge between the theoretical concepts and the practical world. However, where does chemistry get all the answers from? How do the reactions change everything around us so drastically? Well, the answers are stored inside the small nuclei of atoms. Yes, the tiny nucleus inside every atom is like a treasure box. It holds the mystery of several reactions. Now the next question to pop in our mind is, how does the nucleus of a single atom define the reactions in which the atom is participating? That's right, it's the subatomic particles in the nucleus, the protons and the neutrons that are the influencing factors. Yes, the presence and the number of protons and neutrons in the nucleus of any atom define many important characters like the atomic number, atomic mass, isotopic forms, and so on. Wait a second, do we know what these are? What do we mean by atomic number? How is it different from the atomic mass, and what exactly are isotopes? Let's begin with the atomic number first. Atomic number is denoted by the letter Z. As the name suggests, atomic number means the number assigned to a particular atom. Now I want you to think, on what basis should an atom be assigned a number? Should it be on the basis of when the atom was discovered, or on the basis of how much quantity of the element is present in nature? What factor can be applied for numbering the atoms or the elements in general? One promising way is by numbering based on the number of protons present inside the nucleus of the atom. Yes, it's because the atom of every element has fixed number of protons in its nucleus. And this number is unique to every element, right? What do we mean by this? For example, any atom of oxygen always has 8 protons in its nucleus. No other element has atoms with 8 protons in it. That means the number of protons in the nucleus of an atom is like the identity of that element. So can we number the atoms or elements based on the number of protons in the atomic nucleus? Yes, this is how atomic numbers are defined. Atomic number, in simple words, is the number of protons present in the nucleus of the atom. Why do we need an atomic number, by the way? The atomic number helps in defining the characteristics of the element. And why so? Just think about it. We know that the number of electrons is equal to the number of protons in an atom. We also know that the number of electrons will determine the valency and thus the reactive capacity of an atom. So now can we connect the dots? Yes, the characteristics of elements will include a few properties. And these properties will be based on the reactivity of the atoms, right? We also know that the reactivity depends on the number of electrons present in the atom. And the number of electrons is the same as the number of protons. So this is why the characteristics of atoms are largely dependent on the atomic number. That is the reason the atomic number, or simply the number of protons, is important to us. Well, we know that atoms are the fundamental units of every matter. So can you guess what could the size of a single atom be? And do all the atoms of different elements have the same atomic size? Let's study the concept of atomic size in detail in the next video. Atoms are simply defined as the smallest indivisible part of any matter. That means atoms are very small in size. How can we say this? If we take the same example of a wall, then all the bricks that make up the wall are always small compared to the complete wall, right? Similarly, basic units that form a particular matter are always small compared to the complete substance. Now tell me, how big or small do you think a single atom will be? Maybe we can take another small entity and then compare the atom to it. Can we think of an ant? Probably not. Okay, so ants carry little grains of sugar. It means grains are smaller than ants. So maybe we can take a grain of sugar. How about a sand grain, which is smaller than the grain of sugar? But we can still see a grain of sand with our naked eyes. So can you tell me something smaller than this? Yes, we know that microorganisms like bacteria are tinier than what we can imagine, because we cannot see them with our naked eyes. So is an atom as small as a bacterium? You will be amazed to know that a single cell like a bacterium is made up of millions of atoms. Astonished, right? But the fact is that the bacterium can be observed at least using a microscope. However, seeing a single atom is nearly impossible. Yes, the size of an atom is that small. So that means there will be no units to measure it either, right? No, that's incorrect. In spite of the fact that it's so tiny, we still measure the size of an atom with atomic radius. The radius of an atom is measured using units like nanometers. Wait a second, do we know what a nanometer is? In simple words, 1/10 to the power 9 meters gives us 1 nanometer. So does that mean 1 nanometer is 10 to the power -9? Yes, that's how small a nanometer is. And atoms are measured in nanometers. So imagine how small they will be. Now let's take an example of a hydrogen atom. The atomic radius of a single isolated hydrogen atom is around 5 times 10 to the power -11. That's like 0.05 nanometers. Amazingly tiny. Now tell me, if atoms are so small, why do we need to study them at all? Needless to say, they make up the entire globe. Yes, everything that we see around us is made up of atoms. Even our body is made up of atoms. So studying atoms in detail becomes necessary despite their small size. Now, if they are so small, do you think they will have any mass? Think for a moment. If we say that atoms come together to make up matter, and if matter always has mass, it means atoms must possess at least some amount of mass. Yes, although atoms are very tiny, they do have some mass. But how do we calculate the mass of a single atom? Is it practically possible to do so? Is there any weighing scale available to weigh the mass of a single atom? If not, can it be designed? Let's find that out in our next video. Now we are aware of what exactly the concept of atomic number and atomic mass is. Atomic number is simply the number of protons present inside the nucleus of an atom, whereas the atomic mass is the number of protons and neutrons present in the atomic nucleus. So when we have to represent both these entities for an element, how do we write it? Is there a specific way for representing it? Yes. The chemical symbol of the element is written with atomic number at its bottom on the left side, that is in subscript. On the other hand, the atomic mass is written on the top left side in superscript. Something like this. The symbol of the element, its atomic number and its atomic mass. Now, how do we represent a simple element like carbon? That's right, something like this. The atomic symbol, that is C, followed by the atomic number 6 and atomic mass 12 at the respective places. Now, what if it's another element, say chlorine? Something like this maybe? Yes, one type of chlorine atom can be represented like this. Why did I say one type of chlorine atoms? Are there more types of chlorine atoms? Yes, some chlorine atoms have 20 neutrons instead of 18 in their nucleus. Then how do we represent this type? Yes, just like this representation. However, we now need to understand what exactly that is. There are many such cases where atoms of the same element exist in different forms. These forms are called the isotopes. Yes, in simple words, isotopes are defined as the atoms of the same element having the same number of protons but different number of neutrons. Yes, same number of protons but different number of neutrons. Just as we saw in the case of chlorine, all the atoms have 17 protons, but a few of them have 18 neutrons, while some others have 20. So these are the isotopic forms of chlorine. Similarly, several elements have isotopic forms. For instance, we have carbon with 3 isotopes. As we can see here, each isotope has 6 protons, but different number of neutrons. One has 6, the other has 7, and the last one with 8 neutrons. We name these isotopes as carbon-12, carbon-13, and carbon-14 respectively. Now this was about the different forms of the same element. But what if I tell you that atoms of 2 different elements can have the same atomic mass? Yes. Let's understand this with an example. We take 5 different elements: sulfur, potassium, calcium, chlorine, and argon. Now, if you notice, in each case the number of protons and neutrons is different. It's 16 and 24 here, 19 and 21 here, and so on. That's right. However, the total number of nucleons in each sums up to 40. What do we mean by a nucleon? A nucleon is a proton or a neutron. Yes, each thing present in a nucleus is a nucleon. So the total number of nucleons in an atom is the sum of protons and neutrons. We can also say that the total number of nucleons in an atom is its atomic mass. Yes, understand this well. The total number of nucleons, which is nothing but the sum of protons and neutrons, is the same as the atomic mass of the atom. So coming back to our example, there are 5 different atoms here. Though the number of protons and the number of neutrons is different in each case, the total number of nucleons in each is the same, which means the atomic masses are the same. How? Yes, it's simple math. One of the sulfur isotopes that we have taken as an example has 16 protons and 24 neutrons. So the atomic mass of this isotope has to be 40 units. That's 16 plus 24. Next is the potassium isotope having 19 protons and 21 neutrons. So again, we get the atomic mass as 40 units. And similarly, we get the atomic mass as 40 units in each of the remaining cases. Such atoms, or rather isotopes of different elements having the same atomic mass, are called as isobars. The term arises from Greek, iso meaning same and baros meaning weight. Remember, if we consider two isobars, the number of protons and number of neutrons in each case will be different. But the total number of nucleons or the atomic masses will be the same. So far, we've understood subatomic particles and a few important concepts related to atoms. Now, let's move ahead and learn the important concept of valency in the next lesson. In the previous video with a few questions. Let me recall them for you. How do we calculate the mass of a single atom? Is it practically possible to do so? Is there any weighing balance designed to weigh the mass of a single atom? Let us now find out the answers to these questions. Imagine we have two objects A and B. Object A weighs around 12 kilograms is what we know. But we do not know the weight of object B, and that's what we need to find. How do we find that out? We just have a weighing balance with us. Let's put them on either side of the balance and see what happens. Clearly, object A is heavier. Now if we want to find the weight of B, we will need something smaller to compare it to. So let's say we cut object A into 6 equal pieces. And now we compare the weight of object B with one piece. We see that this piece is still heavier than the object B. This probably tells us that we need a smaller piece for comparison. So let's assume we cut object A into 12 equal pieces, which means each piece weighs 1 kilogram. And now when we place them on either side of the balance, we see that it's in equilibrium. Now can we tell the weight of the object B? Yes, each piece of object A here is 1 kilogram. And hence we can say that object B also weighs 1 kilogram. Let me ask you something now. Can we say that the mass of object B is 1/12 that of object A? That's correct. This is exactly how we estimate the atomic mass of an atom. Since we cannot directly calculate the mass of an atom, we usually calculate it with respect to the mass of a carbon atom. We take carbon-12 as our standard. Wait, what is carbon-12? What does it mean? The element carbon has many isotopes and the carbon-12 is one among them. And do we know what isotopes are? Well, for now, we need to understand that they are different forms of the same element. So in the case of carbon, we will have slight differences in the atoms, which is what makes them isotopes. So carbon-12 is one such isotope which is found almost everywhere in nature. Thus, an atom of carbon-12 is considered to be a standard unit and atomic mass is thus calculated with respect to one atomic unit. And how do we define one atomic unit? One atomic mass unit is defined as the mass unit exactly equal to 1/12 of the mass of a carbon-12 atom. So let us assume this is one atom of carbon-12. We divide this in 12 exact equal pieces. We take one piece from this out of the complete unit. Can we say the mass of this single piece is one atomic mass unit? Absolutely. And this is used as a standard to calculate the atomic mass of any other atom. Some examples of this would include the atomic mass unit of hydrogen being 1, carbon being 12, nitrogen being 14, oxygen being 16, and so on. How do we understand this in a simple way? Let me ask you a question. How do you measure the mass of a person? Using kilograms, right? We say that this person's mass is 50 kilograms. Similarly, we say that the atomic mass of oxygen is 16 atomic mass units or 16 AMU. This is how we measure the atomic mass of any atom. The units used are atomic mass units. But do we know what exactly gives the atom its mass? I mean, what exactly is responsible for giving the tiny atom some amount of weight? Let us know more about the concept of atomic mass in the next video.
Or shells around the nucleus of an atom. The actual orbit shapes are a bit too complicated to cover in such a short lesson, but on average, the orbital radius increases as the energy levels increase. In our diagrams, the shell nearest the nucleus is going to represent the lowest energy level or shell, and we draw a circle to depict each shell. We use a dot or a cross to represent each electron, and we'll represent the nucleus by the chemical symbol. Each electron in an atom is in a particular shell, and the electrons must occupy the lowest available shell nearest the nucleus. So, when we are drawing the electron configuration, we have to fill up each shell in turn, starting with the lowest. We'll take a lithium atom as an example. With an atomic number of 3, it must have 3 electrons to balance the positive charge of the 3 protons in the nucleus. It's worth remembering that the atomic number tells you the total number of electrons in a neutral atom. So, we put the first electron into the first shell, and the second. However, this shell can only contain a maximum of 2 electrons. That's one of the rules that you need to remember. The third electron, therefore, must go into the next shell, which we draw as a larger circle around the outside of the first. And that completes the electronic configuration of a lithium atom. The same process of filling up shells applies to larger atoms. You always start with the lowest available shell, and whenever a shell is full, the next electron to be added goes into the next shell. And that's pretty much it. All you need to know is how many electrons can occupy each shell, and at this level, you only need to know the rules for the first 20 elements. The maximum numbers are as follows. The first shell can contain a maximum of 2 electrons. The second shell, up to 8 electrons. The third shell also has a maximum of 8 electrons. And the 19th and 20th electrons go into the fourth shell. And this would actually represent a calcium atom. Note that as we fill up each level, we've been drawing the electrons evenly spaced out on each shell. This is to keep the diagrams tidy and make it easier to count the electrons. And what's more, there's a shorthand way of writing this down. 2, 8, 8, 2. The first number represents the inner shell or lowest energy level. The full stop shows how the electrons are separated between the shells. The second number tells us how many electrons are in the next shell, followed by the third and fourth shells. And so now it's your turn. I'd like you to draw the electron configuration of a carbon atom. Pause the video, find a piece of paper and have a go. And here is what it should look like. It has a full first shell and 4 electrons in the outer shell. Did you get it right? Now, how would you write the electron configuration in numbers for this atom? Pause the video again or rewind if you need to have a think about this. The answer is that it would be written 2.4. And now that you have covered the basics of drawing...
To understand a few concepts related to atoms, let's begin with 2 simple elements, hydrogen and helium. Apart from the difference in the number of electrons and their structure, can you tell me another difference between these two? Yes, the most important difference lies in the fact that hydrogen is capable of reacting with several other elements, while helium never really does. Helium is a quiet, unreactive element that does not participate in reactions. But have you ever wondered why? What makes helium and many other elements also like neon, argon not participate in chemical reactions? And another question we would have is what makes other elements react spontaneously with each other? The answer is valency. Yes, one of the most important factors for reaction is the concept of valency. But before that, let's have a look at an important concept called the electronic configuration. Now, what could this be? As the name suggests, electronic refers to electrons, and the term configuration literally means arrangement or layout. That means the electronic configuration of an atom is the arrangement of its electrons in the shells. As simple as that. There are two facts that we need to recall. First, the innermost shell, or the first shell rather, has a maximum of 2 electrons that can be accommodated in it. Secondly, from the second shell onwards, whichever is the outermost shell, it can accommodate a maximum of 8 electrons. In simpler words, outermost orbital can contain 8 electrons at max. This state is called as the octet state. The term originates from the Greek word octa, which means 8. The octet state is considered to be a stable state. Let's understand this in a simple way. You love chocolates. Now, if there is a bag of chocolates kept open before you, how many will you try to grab at once? Needless to say, you will try and take as many chocolates as your hand can accommodate. That means the maximum number of chocolates is what anybody will wish for. Now, what have chocolates got to do with electronic configuration and valency? Let's understand the relation. As a part of human tendency, we will try and grab the maximum number of chocolates using our hands. Similarly, the atoms would want to have maximum number of electrons their shells can accommodate. That means if it's just one shell like in the case of hydrogen or helium, then the atoms would want to have 2 electrons in it. That will be the outermost shell of the atom. This will help them achieve a stable state. Similarly, for all the other atoms having more than one shell, it's obvious that they will wish to have 8 electrons in their outermost shell. And why is this so? That's correct. It's because the outermost orbital of any atom can accommodate a maximum of 8 electrons in it. That is the reason why all the atoms of various elements are in a constant struggle of attaining 8 electrons in their last shell. That is, achieving the octet state. However, it's not possible for all to have 8 electrons in the outermost shell. Imagine the case of oxygen. It has a total of 8 electrons. So can we just have one orbital around the nucleus containing all the 8 electrons? Absolutely not. In fact, according to the rule, we have to fill 2 electrons in the first and the remaining 6 electrons in the second shell. Because the capacity of the first shell is to accommodate a maximum of 2 electrons. So can we say that the electronic configuration of oxygen is 2,6? That's right. But now this indicates that oxygen does not have 8 electrons in the outermost shell. So how will it achieve its stable state? What can be done to have 8 electrons in the outermost orbital? Yes, oxygen can borrow or share electrons with atoms of other elements, right? Absolutely. This is how chemical reactions happen. Wait a second. Are we saying that chemical reactions occur because atoms of various elements give or take or share electrons between them? That's correct. And is this how compounds are formed? Absolutely. The giving or accepting or even sharing of electrons between the atoms of elements give rise to formation of chemical bonds. This ultimately gives us a compound. Now you tell me, how will the atoms decide how many electrons are to be given or accepted? How will they understand that electrons need to be shared with the other partner? Who decides all this? Well, the answer to all these questions is the concept of valency. Let's understand this important concept in detail in the upcoming video. Can you give me the answer? Yes, it takes place because atoms are always in a constant struggle to reach the stable state. And what is this stable state? Well, if the atoms have only one shell, then the stable state is achieved when 2 electrons are present in it. And if the atom has 2 or more than 2 shells, then the stable state is achieved when the outermost shell contains 8 electrons. It's called an octet. But the stable state is seen only in case of a few elements. We know that elements like helium, neon, argon, etc. have atoms with such desired electronic configuration. But what about the case of atoms which do not have this octet? Yes, they will participate in bond formation. That means they will either give or take or share electrons. But wait, who decides how many electrons will participate in the bond formation? Or who tells the atoms if they've to give or take electrons? Well, the answer to these questions is valency. Let's understand this concept in detail. In simple words, valency is defined as the combining capacity of an element. Now, what exactly do we mean by this? When we say combining capacity, that means how much can an atom bond with another atom. Does that mean how many electrons can be given or taken or even shared? Yes. Does the capacity of an atom to give electrons, accept electrons, or even share them in order to achieve the octet state can be termed as its valency. And what about the case of elements with just one shell? That's correct. Trading of electrons is carried out for attaining 2 electrons in the outermost and only orbital in such atoms. Let us take simple examples to understand this. In case of hydrogen, we have just 1 electron in the outermost shell. That means it has to somehow add 1 more electron to the outermost shell. Thus, we find that the valency of hydrogen is 1 as it accepts or sometimes even shares electrons with atoms of other elements. So, can you tell me the valency of oxygen now? The electronic configuration of oxygen is 2, 6. That means it has 6 electrons in the outermost shell. So, how many electrons are needed to complete the octet? Yes, 2 electrons. Thus, the valency of oxygen is 2. It accepts or takes 2 electrons from other atoms for completing the octet. Now tell me, what will be the valency of magnesium? We know that magnesium has 12 electrons. That means the electronic configuration of magnesium is 282. So how many electrons will be needed now? 6. That's correct. And that's what we're able to see. 6 electrons are needed to complete the octet. But which atom will give away 6 electrons so easily? Is it even possible? Not really. Then how will magnesium complete its octet? This is where the concept of donating electrons comes into the picture. If managing the gain of 6 electrons is difficult, then can it think of giving or donating the 2 electrons? Yes, absolutely. So if magnesium gives away 2 electrons from its outermost shell, then we say that the valency of magnesium is 2. That means it's not only about how many electrons can be taken, but also about how many electrons can be given by the atom. That is how we calculate the valencies of various elements. Now, to understand the concept better, let's take an example of elements forming one compound. Maybe we can think of sodium chloride. For the formation of one molecule, we need 1 atom of sodium and 1 atom of chlorine. What are the valencies of each, by the way? Sodium has the electronic configuration 281, while chlorine has an electronic configuration 287. Before I tell you what happens, I want you to give it a shot. What do you think will happen? Doesn't this indicate that sodium will donate 1 and chlorine will accept 1 electron to complete their respective octet state? Yes, that's absolutely correct. And that is what helps in the formation of sodium chloride molecule. Chlorine needed 1 electron which it got from sodium, and sodium gave 1 electron as it was the easiest way to achieve stability. So the valency of both sodium and chlorine is 1. Does this mean that only elements having the same valency always combine together to form a bond? Not really. Just take the simple example of a water molecule. We have seen that the valency of hydrogen is 1 while that of oxygen is 2. Here, hydrogen needs 1 electron while oxygen needs 2 electrons. Both need electrons. So how do the atoms combine in this case? How will the bond formation take place then? Well, they will both share electrons with each other. But how? It's not that straightforward. We will understand it in one of our future videos. For now, we have to know that one atom of oxygen combines with 2 hydrogen atoms to give us one water molecule. This is how atoms with different valencies combine with each other to form compounds. Now that we know how the concept of valency works, let's have a look at how the atoms come together to form independent units. Let's discuss the concept of molecules in the next video. Aware of the difference between elements, compounds and mixtures. Do you remember the differences? Mixtures are like food items that we consume. They contain everything in proportion that we desire. We can add or remove a substance according to our need. Compounds, on the other hand, are those which have substances in fixed proportion. So if you change the proportion of substances, it will affect the compound and render it changed. For instance, if you remove even one hydrogen from H2O, that is water, the composition changes and water as a compound does not exist. Thus, fixed proportion is a must in compounds. Lastly, we have the elements. These are the purest forms of any known substance. They are composed of only the same type of atoms. There are neither proportions nor random mixing of substances. So can we say that compounds and mixtures are made up of elements? Absolutely. So in nature, it implies that elements are the basic forms of every material that we find around. And hence, in order to study every substance around us, we need to begin with studying the various elements. So where do we begin? Maybe the reactivity or maybe the physical properties first, right? I'm asking if we can study the reactivity and physical properties of each of the elements. Is that feasible? Well, all these would have been valid only if the elements would be few in numbers. Do you know the number of elements that exist? Astonishingly, the number of elements that we find naturally occurring is 98, while the total number of elements known to mankind is 118. So how do we study each element individually for all its properties? Looking at the number of elements that exist, I don't think it would be convenient to pick every element individually and study all the properties, right? Imagine you have to organize the kitchen. You will not place any vessel or eatable randomly anywhere. You will organize the shelves and refrigerator in the most convenient way which is suitable for your needs. Similarly, for studying so many elements, we need to organize them appropriately. An organization begins with arrangement. Yes, arranging the various elements is the first step towards understanding their properties. And arrangement is possible only if we categorize them, right? This is how we organize the elements. And this process of categorization helps us study the elements with ease. In other words, we've classified the elements here. Classification of elements is categorizing the various elements into groups based on similarities and differences in their properties. The classification system helps us in grouping the various elements into categories which we refer to as the periods. Hence, the system is also referred to as the periodic classification of elements. Let's get to know how periodic classification was carried out in the early days of emerging chemistry when not many elements were known to people. In the upcoming videos, we will understand the various classification systems put forth by the different legendary personalities. Dmitry Ivanovich Mendeleev played quite a legendary role in the field of chemistry. He not only gave us the simplest and the most efficient method of grouping elements, but also laid the foundations of periodic classification of elements that we use today. So in this video, let's dedicate some time to understand what and how Mendeleev actually worked on. When Mendeleev began his work of grouping the elements and arranging them, There were almost 63 elements known to him. He was firm on the thought of arranging the elements with respect to their physical as well as chemical properties. He knew that for understanding the chemical properties, he would need to make them react with one or two standard elements. For this, he chose hydrogen and oxygen. But why? Mendeleev thought of making the elements react with hydrogen and oxygen because of the following reasons. They are very reactive, they are found readily, and they form compounds with most of the elements. Yes, this helped him understand the chemical properties of all the reacting elements. Later, in order to simplify the process, he wrote all the physical and chemical properties of each element on 63 different cards. Now, all he had to do is arrange these cards. But that wasn't so simple. So he started arranging the cards in the increasing order of their atomic masses. When he was done pasting all these cards on his wall, he had two astonishing observations. One was that there were a few empty spaces left in the complete table that he formed. These positions belonged to the elements that were not yet discovered. But Mendeleev had a firm belief that the missing elements did exist and are yet to be discovered. Not only this, but he was so confident about the characteristics of these elements that he predicted their properties well in advance. Later on, when the elements were discovered, it was found that the properties predicted by Mendeleev were almost a perfect match. Second observation that Mendeleev had was the recurrence of the physical and the chemical properties of these elements. When arranged in a systematic manner, it was found that the physical and the chemical properties of elements recurred at a particular interval of frequency. With this, Mendeleev came up with a law. He named it as the periodic law. The law stated that properties of elements are periodic functions of their atomic masses. Now, what do we exactly mean by this? Let's simplify this by breaking the statement in parts. Properties of elements means the physical and the chemical properties of all the elements in the table. Are the periodic functions means those which occur at regular intervals. And lastly, of their atomic masses means when arranged in the increasing order of their atomic masses. So can we simply say that when elements are arranged in the increasing order of their atomic masses, they show similarities in the physical and chemical properties at regular intervals? Yes, that's what Mendeleev meant. This is how Mendeleev laid the foundations for the modern periodic table. But did this great contribution by Mendeleev have no limitations at all? Well, there were a few that emerged with time. Let's discuss the achievements and the limitations of Mendeleev's work in the next video. The table put forth by Mendeleev was quite well defined, but it wasn't the best table ever. Why do I say so? It's because with time, the number of elements being discovered increased, and fitting them into the table according to the periodic law by Mendeleev seemed difficult. Also, we have taken a look at the major limitations of the periodic table by Mendeleev. So with all these limitations, how do we study the elements? How do we carry out the periodic classification? Well, if the elements discovered later did not follow the periodic law given by Mendeleev, then the only way to arrange them was by modifying the law. Yes, this was, however, not what scientists could think of as the first step. It was quite gradually that the scientists realized the fact that the law could be modified. But how did this happen? It was around 1913 that the British physicist Henry Moseley found an interesting fact. He realized that instead of atomic mass, all the elements will show periodicity if arranged on the basis of their atomic numbers. Wait a second, did I just say atomic number? Isn't atomic number a randomly assigned number to the atom by us? Actually not. Atomic number of any element is never a randomly assigned number. It is basically the number of protons present in the nucleus of the atom of that element. For instance, let us consider the first 4 elements in the table. So we get atomic numbers of hydrogen as 1, helium as 2, lithium as 3 and beryllium as 4. So why are these elements assigned these particular atomic numbers only? Can we change these numbers ever? No, we can't. That is because they have these respective numbers of protons in their nuclei. Hydrogen has just 1 proton in its nucleus. Similarly, helium has 2 and lithium has 3. And how many protons will beryllium have? Correct, it has 4 protons. The same is valid for other elements as well. Coming back to the table, did Henry Moseley think that characteristics of elements are based on their atomic numbers and not their atomic masses? Yes, that's what he meant. And with this, there emerged a new law of studying the periodicity of elements. It was called the modern periodic law. The law stated that the properties of elements are periodic functions of atomic numbers. So what does this mean? This means that the physical and chemical properties of elements do occur periodically. But this happens when the elements are arranged according to their atomic numbers. All the known elements could be arranged based on their atomic numbers. With this, predicting the properties of elements yet to be discovered got simpler and more precise. This helped in placing the newly discovered elements properly in the periodic table. Also, overcoming the limitations of Mendeleev's table was another advantage. And how did that happen? Do you remember the limitations? The first limitation of no precise position for hydrogen was mainly overcome. It was assigned a position that would not lead to any confusion. We will take a detailed look at this position of hydrogen later in the higher grades. Next limitation of the Mendeleev's table was the position of isotopes. Can you recollect what isotopes are? Yes, they are the atoms of the same element with different number of neutrons. That is the reason why, in spite of belonging to the same element, the atoms have different atomic masses. Because atomic mass is the sum total of all the protons and neutrons present in the nucleus. Placing isotopes in the table was a limitation. But as we know, in the modern periodic table, the position of elements was no longer based on atomic masses. They were based on atomic numbers. An atomic number is given by the number of protons. That means the different number of neutrons will not be a worry for us. So it was possible to place the isotopes now. Because all the isotopes of any particular element could be placed at one single place. And this place would be the position of that element in the table. So now can we say that chlorine 35 and chlorine 37 will be placed together? They both have 17 protons, which means they will have the same atomic number. Hence, they will be placed together. Lastly, we had the prediction and placement of undiscovered elements. The previous table by Mendeleev was based on atomic masses of elements. However, the atomic masses of elements were not arranged in a constantly increasing order. Hence, if newly discovered elements were to be placed in the table, then their position would be confusing. But why? It's simply because if the atomic masses of previously discovered elements were not in a regularly increasing manner, then how and where will we place the new ones? Just for the sake of understanding, let us assume some values for the atomic masses of two elements. Element 1 has atomic mass 300, whose position comes first, while element 2 has an atomic mass 297, which is placed later in the table, that is, after element 1. Now in this case, if a newly discovered element, say element 3, has atomic mass of 299, where will we place it? Between the two elements or after the second element with atomic mass 297? And this is what was happening with Mendeleev's periodic table because the atomic masses of elements were not placed in a constantly increasing manner. Some elements did have atomic masses less than the previously placed element. So placing the newly discovered elements will disturb the entire table. But in the modern periodic table, the position of elements was based on atomic numbers. So newly discovered elements could be easily added in between. Because the atomic numbers of elements are found to occur in a constantly increasing manner. This is how the important limitation of Mendeleev's periodic table got ruled out. And that is the reason why the new periodic table surfaced as the most useful tool for studying elements. The newly arranged table of elements was based on the modified law. Do you remember the name of this important law? Yes, it is the modern periodic law. So can you guess the name of the table that was based on this law? Yes, it was called the modern periodic table. Now let's have a detailed look at this modern periodic table, its properties, and a few of its important characteristics in the upcoming videos.